So we're ready to summarize the process for estimating an unknown population mean and making the choice of either using a z-interval or t-interval. So everything will be based on whether or not sigma, the population standard deviation, is provided to us. So if it is known, so the answer there is yes, it says that the critical values z alpha over 2 apply. And if we are going ahead and using technology rather than the formula, we can use a z-interval in this case. So z applies when we know sigma, and if we do not know sigma, the t alpha over 2 critical values apply. And if we're using technology, that is our t-interval. And in both cases, if our sample size is small, so anything under 30, we're considering a small sample size, then the original variable that we're studying must be normally distributed. So let's take a look and see if we can identify the difference and the effects of using a z versus a t interval. So number one, a Maine lobster trapper wishes to estimate the mean weight of his catches. He records the weights of 6 randomly caught lobsters and finds the mean weight to be 1.8 pounds. Assume lobster weights are normally distributed with a standard deviation of 0.6 pounds. All right, so we're creating a confidence interval estimate for a mean. So we know we have a decision to make, z or t, and we'll be rounding to 1 decimal place. All right, so let's get the symbols down. So we're estimating the population parameter mu, and we know that our best point estimate will be the corresponding sample statistic, in this case, x bar, the sample mean. So let me start at the beginning with given values. He recorded the weights of 6 lobsters. So there's our lowercase n, our sample size is 6. And that would be considered a small sample size. And that's why this sentence that starts with assume is important. So assume that weights are normally distributed. So that's just our requirement in order to continue with either z or t. All right, so when he takes his 6 lobsters, he gets a mean of 1.8. So there's our sample mean. And assume weights are normally distributed with a standard deviation of 0.6 pounds. So the question is that standard deviation for the 6 lobsters, or does that sentence simply say it's true in general? So in that sentence, it specifically says we're going to assume that this is true. So if we're assuming that it's true, what they're telling us is that we are allowed to say we know that the population standard deviation is 0.6 pounds. So if it doesn't say the standard deviation is for the 6 lobsters, then it's not. So that's the general guideline. So if it doesn't say the numbers are related to the sample data, then we assume they're the values for the entire population. So we know the sigma value, and this is why a z-interval applies. So we are able to do a z-interval because we're estimating a mean and sigma is known. Okay, so let me go ahead and create that interval. So stat tests, number 7 is our z-interval. So we have our sigma, our x bar, our n, and we're creating a 95% confidence interval. And we'll round to 1 decimal place, and lower limit then would be 1.3, less than mu. What we're estimating, we believe that mean is between 1.3 and 2.3. All right, I'm going to draw the picture here. So our lower limit, our upper limit, and our point estimate. So there's our sample mean, our lower limit, and our upper limit. So the interval is based on knowing x bar, but our answer is what we think mu is. Mu is what we're trying to estimate. All right, I'm also going to include the margin of error here before we write the sentence. So the margin of error is that difference between the point estimate and the lower upper limits. So this distance is 0.5. So we've got a margin of error of 0.5 pounds. Okay, I'm going to write that confidence interval in this form just to review. So we could have said, we believe that the mean weight of his catches is 1.8 pounds plus or minus 0.5 pounds. All right, so our sentence based on a sample of 6 lobsters, we estimate with 95% confidence that the true mean weight of his lobsters is somewhere between 1.3 and 2.3 pounds. All right, so let's compare that to the next example. So I'm going to just highlight a couple of things here. So our accuracy is our margin of error. So we are accurate to within 0.5, and again, units are pounds. So we think this is the answer for all his lobsters, on average 1.8 pounds, and we are accurate to within 0.5 pounds. Okay, so what we want to see is what happens if we know less about the population we're studying. So the next question is going to sound very similar, but you'll see what I mean by saying we know less about our population. So number 2 here. So a Maine lobster trapper wishes to estimate the mean weight of his catches. So I'm not changing the initial parameter we're estimating. And so our best point estimate will be the sample mean. He records the weight of 6 randomly caught lobsters and finds the mean weight to be 1.8 pounds with a standard deviation of 0.6 pounds. So let's talk about that given information. So lowercase n, our sample size, the number of lobsters was 6. And for those lobsters, those 6 lobsters, the mean came out to be 1.8 pounds. And it had a standard deviation of 0.6 pounds. So when you read that sentence, for these 6 lobsters, this was their mean, and this was the standard deviation. So that standard deviation isn't for all of the lobsters. It specifically says for these 6 lobsters, he finds this mean with this standard deviation. So we are in the habit of always thinking standard deviation is sigma, because prior to chapter 7, we were often given sigma. But now we're seeing that standard deviation sometimes is the standard deviation of the sample. So rather than sigma, that is S. So sample standard deviation, and I'm going to just write it in words as well. So S, sample standard deviation, and in this case, again, 0.6 pounds. So the given information is similar, but we don't know sigma. So we don't know something about our population. Therefore, we're going to end up seeing bigger margins of error in our estimating. So when we don't know sigma, so the TI interval that applies, if we don't know sigma, we rely on the T distribution, and on our calculators, technology will be a T interval because we're estimating a mean, and sigma is unknown. So you have to pay attention to standard deviation. It is not always sigma. It's sigma for population, and it's S for sample standard deviation. All right, but all other components remain the same. So by not knowing sigma, we should see a larger margin of error because we're going to use the same confidence level. All right, so we'll check it out. So stat tests, and we'll do our T interval. And this time it will ask us for S, sample standard deviation. and nothing else is changing. And we'll round to 1 decimal place. So that will be a lower limit of 1.2 less than mu. So 1.2 less than mu less than 2.4. So we'll take a look at that graph. So our point estimate was 1.8. And now our lower limit, instead of 1.3, we're going lower. We're going to 1.2. And instead of 2.3, we're going higher. We're going up to 2.4. So our margin of error is larger. Now this difference is 0.6 pounds. So let me write this in our second form. We could say that we believe that the mean is 1.8 pounds, but now we've lost some accuracy because we believe this is true, accurate to within 0.6 pounds. All right, so that is the difference, Z versus T. If we don't know something about our population and we have to rely on a sample standard deviation to estimate that sigma, we end up with larger margins of error when we are estimating. So we'll write this sentence to wrap it up. Just going to highlight here. So we got bigger margins of error. And based on a sample, now we can say with 95% confidence that now we've created a larger range of possibilities, 1.2, between 1.2 and 2.4 pounds. All right. And that, what I call the Lobster page, summarizes estimating a population mean.